Here's a question from the homework from 16.2 that was asked, and it is often asked because it's not often clear to students what's going on here. So the idea is that we have this curve C, and we're going from 1, 1 over and up. That's our goal. And this curve is in the midst of some vector field, so there's vectors all over here. What we're trying to figure out is to approximate the work done by that vector field in moving this curve. So what this problem is really getting at is whether or not you understood the derivation of that work line integral. What we do when we derive that is we look at a given point and we look at the force at that point. And we partition this up into pieces. So if I partitioned a piece here, let's say this long, and I decided for that whole length there, let's suppose that this is the one force that acts on this whole length. Remember that work is force times distance. So we would take the projection of this force in the direction of travel. So the projection is going to be this red length here. So the projection of that force, the force in the direction of travel, is 2. If you just do it by way of the number of squares there, that would be the horizontal component is 2. The length, the distance that we're moving is 2. So on that one piece, the work is force times distance, which is 2 times 2, or 4. We do that on each of these pieces. So this next piece, we'll start here and we'll go till the next force. That's a distance of 2. We take the projection of this force onto that direction of travel there, and we get this force in the direction of travel, this horizontal force, which is 2. And so the work on that subinterval is 2 times 2, or 4 as well. Now, I think this problem would be much more interesting if you're going to see these are all going to be 2 times 2. It'd be more interesting if they weren't, and I think it'd even be more clear to see if you understood what's going on. But as we go around, here's what we're going to get the same thing. Here, the distance is 2. I'm just going from one force to the next. So the distance is 2, and the component of force in that direction happens to be of length 2. And so the work is 4. It'll change when we go around the corner. Next piece. Also length 2. So the distance is 2. The component of force in that direction, dropping a perpendicular, is 2. And so the work on that subinterval is 4. Now we're turning the corner and going this way. Okay, so if I go from this force to the very next force, so I'm going to take this path here. So that distance is 2, but something changes this time. I want the projection of that force on that direction of travel. So this time I'm going to project my force down to that green segment. And so the vertical force here, that's the component right there. And that this time is only length 1. So the force there is 1. And so the work on that subinterval is force times distance, which is 2. Next piece. Similarly, from this force to the next one, the distance is 2. I take the component of force in that direction of travel. It's 1. So the work on that piece is 2 times 1, or 2. Last stretch there. From here to the end is a distance of 2. The projection of force is once again 1. So the work on that piece is 2 times 1, or 2. Now, as I said, I think it would be much more interesting if these forces were all different projections and if these pieces were all different lengths. But the main idea of this problem is for you to understand what we're computing when we're computing work. It's force times distance. Okay, so the total work here then would be to add up all these. 4 and 4 and 4 and 4 and 2 and 2 and 2. That would be the answer to this one. Hope that helps.